So, we will continue solving more mass transfer problems in this session also. So, first problem, this is a 2 marks problem, the rear of gate question that is not noted. For a, what is the problem? For a 2-phase feed where 80% of the feed is vaporized under column condition. So, Q is definitely 1 minus 0.8, that is 0.2, that is the liquid fraction of the feed, right. The feed line slope in the McApthilly method for distillation column. It is a very easy problem. Feed line slope is minus Q divided by 1 minus Q. So, minus 0.2 by 0.8 minus 1 by 4. Okay. Next, it is 2015 2 marks problem. A problem on distillation. A binary feed consisting 25 mole % liquid and 70 mole % vapor. So, Q is equal to 0.25. Is to be separated in a single stage distillation column. So, it is a flash unit. Right. The mole fraction of more volatile component in the distillate product is 0.95. So, Y equal to 0.95. The molar flow rate of distillate is 50% of the feed flow rate. So, V equal to 0.5 F, and McApthilly method can be used. The Q line intersects the operating line. Q line in a single stage, no? It is a staged unit that have staged unit. That is why I was confused that when it is stated McApthilly. So, it is a staged unit. Q is equal to 0.25. And this component in the distillate is 0.95, the molar flow rate of the distillate is 50% of the feed flow rate. McApthilly method can be used. The Q line intersects the operating line of the enriching section. Q line and operating line, enriching means rectification. Intersection or intersects at 0.35, 0.5, right, in the XY diagram. The slope of the stripping section operating line, that we have to find out. The slope of the stripping section operating line we have to calculate. So, in this type of problem, it is always suggested that you draw the diagram of Y and X. So, this is the 45-degree line, this is equilibrium line, here we have the feed point ZF, and this is the Q line. An operating line here is this XD, and this intersects at the point P, right. And Y is equal to 0.95. So, this coordinate is 0.95 comma 0.95. So you see that Q line and operating line intersection point we know, and V is equal to 0.5 0.5 this F. So I have to know the bottom product composition, and definitely that is the operating line for rectification, sorry, the stripping section. So one of the point is known, and that is this point is 0.35 comma 0.5. Right. So you see that if I write F is equal to V plus L, so L is also 0.5 F and same as V, right. So F ZF is equal to V into Y plus L into X. So ZF is equal to V into YD plus L into this XW, right. So ZF equal to 0.5 into YD, YD is given 0.95 plus 0.5 into XW. So you have to solve for this ZF. This point has got a location of ZF and ZF. Now how we can do that? The slope of Q line is minus Q by 1 minus Q, right. So Q is 0.25, so 0.25 divided by 0.75 minus 1 by 3. Now one of the point on the Q line is known, and this is ZF ZF. So what you can do, we can write that ZF, this coordinate, because it is on the 45-degree line, it has got a coordinate ZF ZF, and this point is known. So ZF minus 0.5, that is a Y, divided by ZF minus 0.35 is equal to minus 1 by 3. So 3 ZF minus 1.5, 3 ZF minus 1.5 minus ZF plus 0.35, right. So here 4 ZF becomes 1.5 plus 0.35, 1.85. So ZF can be solved as 1.85 by 4. So ZF, if I substitute here, I will know XW, and the slope of the stripping section operating line, this is known, this point we have got, that is XW. So it is 0.5 minus XW divided by 0.35 minus XW. So that's all. So in this way we can solve this problem and can get the operating line slope of the stripping section. So what is very important to note, that through this Q line slope and knowing this point, we have to determine ZF, right. So next problem. 2018, a 2 marks problem. A binary distillation column is designed by McAfee method to get a distillate mole fraction of 0.9. So YD equal to 0.9. The enriching section operating line has an intercept with y-axis. So you know that when the enriching section intersects this y-axis, the intersect is xd divided by this, or yd, this yd or xd, whatever, right? It is xd rather. So xd, because we consider a total condenser here, but that's immaterial. So xd divided by this Rn plus 1, because you know this operating line yn plus 1 is equal to r by r plus 1 xn plus xd divided by r plus 1. So this is the intercept, right? This is the equation of operating line for rectification section. So xd divided by r plus 1, the intercept is 0.3, right? The ratio of liquid to vapor molar flow rate in the enriching section we have to calculate. So 0.9 by 0.3 equal to r plus 1, which is 3, so r is equal to 2. And ratio of the liquid to vapor flow rate is basically nothing but the slope of the operating line, because we know that for all mass exchangers the operating line slope is r by this L by V, right? So this is r by r plus 1. So it is 2 by 3. That's the answer. Next, this is 2011, a linked question. 2 plus 2, 4. A binary feed mixture containing equimolar quantities of S and T. So S plus T, ZF equal to 0.5. Is to be distilled in a fractionating tower at atmospheric pressure. So here 1 atmospheric pressure we have. The distillate contains 96 mole percent S. So xd or x distillate equal to 0.96. We are writing in terms of S. S is more volatile. Why? Because it is having a higher mass fraction in the distillate. The Q line intersects the equilibrium line. So Q line and equilibrium line intersects at x prime is equal to 0.46, y prime equal to 0.66, right? Assume that McAfee method is applied and relative volatility is constant. First we have to calculate the minimum reflux ratio. So you see, if I draw this y versus x diagram of this system, this is 45 degree, this is equilibrium line, and we have xd is equal to 0.96, equimolar mixture, so ZF is here 0.5, and that's the Q line, where Q line intersection point, this point is 0.46, 0.66. So this point, as it is given directly, we know that operating line for the rectification section must pass through this point of intersection in case of minimum reflux ratio, right? So generally in graph we solve from the intercept, but here we are not allowed to draw the graph. So we have to calculate it from the slope because we know these two different points. So slope is 0.96 minus 0.66 divided by 0.96 minus 0.46, which is R minimum divided by R minimum plus 1. So it is 0.3 divided by 0.5. So it is 3 by 5 R minimum divided by R minimum plus 1. So 3 R minimum plus 3 equal to 5 R minimum. So 3 divided by 2, right? Right, here. 3 divided by 2 is equal to R minimum, 1.5. That's the minimum reflux ratio. And the options are given as 1.6, 1.5, 0.66 and 0.6. Now the feed, next question. The feed is at its dew point, at bubble point, superheated vapor and partial vapor. So you see, what will be the cases? If, let's discuss it. If it is a vertical line, it can happen when Q equal to 1. So it is saturated liquid, right? This is saturated vapor. This is superheated vapor. And this is subcooled liquid. So obviously here let's directly calculate it. So you have slope is equal to minus Q by 1 minus Q, right? So minus Q by 1 minus Q is minus, this minus Q by 1 minus Q is 0.5 y minus 0.66 divided by 0.5 minus 0.46. So it is 0.04 and with a minus sign, sorry, not 0.04, this 16 and this is 0.04, right. So the slope is equal to minus 4. So Q by 1 minus Q is equal to 4. So Q is equal to 4 minus 4Q. So 5Q is equal to 4. So Q is equal to 4 by 5, that is 0.8, which is less than 1 and greater than 0. So it is a two-phase, right? Because we know for two-phase Q is less than 1, greater than 0. For saturated liquid, Q is equal to 1. For saturated vapor, Q is equal to 0. For superheated vapor, Q is less than 0. And for subcooled liquid, Q is greater than 1. This we have discussed. So based on that, we can actually solve this. This is a theory question. See, the equilibrium moisture curve for a solid is shown in the figure below. What is that? And these are marked, like this is 3. Say this is xi and the curve is x, this is 4, okay. Say h here, this is 1, this is 0 and this is 1 up to this is 2. The total moisture content of the solid is xi initially, and it is exposed to air of relative humidity H. So if the table below, group 1 lists the types of moisture and group 2 represents the region in which in the graph above. So group 1 contains equilibrium moisture, bound moisture, unbound moisture and free moisture. And group 2 contains 1, 2 and 3, 4. So it's simple identification of what is equilibrium moisture, what is free moisture, what is bound moisture and what is unbound moisture. So definitely here, as it is an equilibrium curve, so you can understand that this one is equilibrium moisture, 2 definitely is a free moisture which can be removed. Now when the exerted vapor pressure of the water vapor by the solid is less than the pure water's vapor pressure, then we call it bound moisture. So here up to this, the exerted vapor pressure is less than that of Psat. So 3 is the bound moisture, and whatever is above and over bound moisture is the unbound moisture. So 4 is the unbound moisture. So that was the 2 marks problem, and it's 2009, a 2 marks problem. Right. Simple identifications of all the different moisture components. So next, this 2013 2 marks problem. A cross current cascade of n ideal stages is used to treat a feed stream of molar flow rate E. So we have 1, 2, n. Molar flow rate is E. The feed stream contains a solute which is to be recovered by PO solvent having a molar flow rate S. Right. So we have a molar flow rate S total. The solvent is divided equally between n stages. So you are giving the solvent to all stages equally. So the amount is obviously S by n, S by n. Or let's draw an ith stage here, it's better. Right. The linear equilibrium curve relating the mole fraction x and y star of the solute in raffinate and the extract phases is given by the equilibrium relation is y star is equal to mx. Assume dilute condition, the ratio, that means the molar flow rate of the raffinate and extract are not changing from one stage to another stage. The ratio of the solute mole fraction in the original feed to that in the exit raffinate. So we have to solve for x0 by xn, right, and 4 different expressions are given. So you see that if I write it for the ith stage, here this is x0, so obviously this is y1, this is x1, this is y2, this is x2, this is xi minus 1, yi, xi, this is xn minus 1, yn and xn. Fine. So if I draw this ith stage, here we have f e with xi minus 1 going e and xi. Here s by n ys is equal to 0. Here s by n yi. Right? So if I write the balance, so it is E xi minus 1 minus xi is equal to s by n into yi, which is s by n into m into xi. Okay? So you see this xi minus 1 by xi minus 1 is equal to m into s divided by n into e, or rather xi minus 1 by xi is equal to 1 plus m into s divided by n into e. So we have to solve for x0 by xn, so which is x0 by x1, x1 by x2 up to xn minus 1 by xn. So obviously all these ratios are same and there are n number of stages, so it is 1 plus m into s divided by n into e to the power n. Right? 1 plus m into s, that is option A. So that is option A, so you have got the answer. Next, it's our distillation problem. It's a batch distillation problem. It's 2013 2 marks problem. The vapor liquid equilibrium curve of a binary mixture AB may be approximated by a linear equation over a narrow range of liquid mole fraction. So XA for 0.3 less than 0.2. Generally the relation you know that y is equal to, we know that alpha x plus 1 minus alpha minus 1 by 2x. But over this narrow range of 0.2 to 0.3, it can be safely approximated by a linear relation which gives ys star is equal to 1.325 xa plus 0.121. Right? So ys star is a mole fraction of A in the vapor phase. 100 moles of feed. So F is 100 and XF is 0.28. Is batch distilled to a final residue, XW is equal to 0.2. Using Raleigh's equation, the number of moles in the residue left behind in the distillation unit. So number of moles in the residue we have to calculate. We know the Raleigh's equation states that W by F is equal to integral xf to xw dx divided by y minus x. There is nothing in the problem, simply you have to substitute. So ln of W divided by 100 moles are given, xf is equal to 0.28, xw is equal to 0.2, right, dx divided by 1.325 x plus 0.121 minus x. So it is 0.28 to 0.2 dx by 0.325 plus 0.325 x plus 0.121. So that's equal to 1 divided by 0.325 ln of this. So that is 0.325 into 0.2 plus 0.121 divided by 0.325 into 0.28 plus 0.121. So this you calculate, definitely it's coming to be negative because W is lower than 100 and from there we can solve for W. . . . So next, this is quite an interesting problem. You see, this is 2015 2 marks problem. So multi-stage countercurrent liquid-liquid extractor is used to separate solute C from a binary mixture F of A and C. Pure solvent B is recovered from the raffinate, that is a typical raffinate cleanup column, by distillation as shown in the schematic below. So let me draw the schematic. So this is the multi-stage extractor. So here we are giving F, which is basically A plus C. We generate the extract. Now we have the raffinate R, and raffinate goes to the distillation unit. Giving product P and solvent B, right, and here you are adding pure solvent B. That is the schematic, right. So here, why, if that is definitely not a part of the problem, why we are getting B here? Because A and B, A is the carrier, C is the solute, B is the solvent, right. So A and B are appreciably miscible. So that is why we have a lot of solvent in the raffinate phase, which we have to regenerate back. The product here is basically A, right. So the thing is, actually we are removing certain impurities by distillation, because E we are not going for any treatment, right. E we are not treating according to this problem schematic, that we have a multi-stage extractor A and C. C is the impurity which is present in the stream, right. A is the valuable product. So that is why, because raffinate contains majorly A, plus there will be some amount of B, and C has been removed. So we are getting the product. Maybe there is a little bit of C, and we are regenerating the solvent. Fine. Location of different mixtures for the process are indicated on the triangular diagram below. P is the solvent free raffinate, E is the extract, F is the feed, delta is the difference point, which is indicated in the graph. The line PB intersects the binodal curve at U and T. The line P delta and FB intersects binodal curve at V and W. So let us first draw whatever is given in the problem statement. So this is the triangular diagram, right. This is A, this is B, this is the triangular diagram, and this is the delta point. So delta point is connected to this and to this, right. This is F, this is P, this is W, this is E, and F is connected also to B like this, and B is connected to P also, and this intersections, this P delta intersection, this top is V, the bottom is this point is U, and FB, here this point is T, right. So what is the question? The raffinate coming out from the extract is represented in the diagram. The raffinate coming out from the extractor, this R is which one? Okay. From the diagram, and the options are T, U, V and W. So you see the raffinate coming out from here must be lower than that of feed, okay, that we can understand. So it can never be T, okay. it can never be T, and neither it can be W, because F and this E intersection can never be the raffinate composition here. Okay? So, it can never be W. So, the choice is between V and U. Okay? V and U. Now, P is the product. P is not the raffinate. P is the product. P is not the raffinate. P is the product. And what is important to note, that actually in order to solve this problem, you do not have to know the triangular diagram for a multi-stage extraction process. What we get? R is getting split into P and B, right. So, if I mix P and B, I must get R. So, you see in the relevant phase space, if this is P and this is B, the composition of R must be on the joining line of P and B. So, V is on the joining line of P and delta, whereas U is on the joining line of P and B. So, my answer is U. Okay. And this is the typical this tie line, this is not the tie line, the lever arm rule concept is derived from here. The amount of P and amount of B is equal to this amount of this length section RB by length section PR. So, though we do not require this lever arm rule, but from this idea that in the relevant phase space, if I located a solution as point 1 and another solution at point 2, and we are mixing these two solutions, the mixture's composition must be lying on the line joining point 1 and 2. So, here P and B, if I join or if I mix, I will get back R, because R is split into P and B. So, P, B joining point must contain R. So, U is the and as it is raffinate, it must be on the, just like if I say that this is U, this is R, it can never be. Why? Because it must be on the raffinate arm of the binodal solubility curve, and U is on the raffinate arm, so it is U. Okay. So, basically here the problem is, without going by anything, even if I do not know this extraction, simply by looking at R is splitting into P and B, we can locate from here that U is basically the representative point for R. Okay. Let us solve another problem, 2. This 2008 2 marks problem. Let me draw the schematic first. So, that is the diagram. What is the statement? The feed F containing a solute is contacted with a solvent S in an ideal stage as shown in the diagram. Only the solute transfers into the solvent. That means the carrier and the solvent, they are immiscible. So, we have to go for solute free bases. The flow rates of the streams are shown on the solute free basis as I have mentioned and indicated by the subscript S. So, Fs, Ss, Rs, Ps, they are all solute free terms. So, if I consider this A and C and solvent is B, right. So, this is pure A, this is pure B, only solvent C is transferred from this stream to this stream in this extraction device. Okay. The flow rates indicates the composition of the streams are expressed on mole ratio basis. That is why capital X and capital Y. The extract leaving the contactor is divided into two equal parts, right. So, this is PS, this also is PS, and composition is also Y out because it is same composition. One part collected as product as it is shown, the other stream is recycled to join the solvent. The equilibrium relation is Y is equal to 2x, right. Now, what we have to find out? The product flow rate PS and its composition Y out, okay, in a single question. Now, you see that immediately you will get confused that what to do with the recycle. But if you think of this cascade, right, and write a material balance, immediately you can understand that this is pure carrier flow rate 100 moles, this is pure solvent flow rate, and the flow rates are expressed in solute free basis. So, solute only is getting transferred from this phase to this phase, right. So, obviously, we can notify or we can conclude that Rs is equal to 100 mole per second and PS is also equal to 100 mole per second. So, first answer PS 100 mole per second. Now, second, what about Y out, right. So, do not think about this recycle again. We have an inflow, so we have to write a component balance. So, Fs into X in is equal to Rs into X out plus PS into Y out, right. And these two compositions definitely they are in equilibrium, because here these two are in equilibrium because they are just moving out from the extractor. Now, here splitting. So, definitely these two must be in equilibrium. So, Fs into Y in, and actually this Ss into Y in, so that is 0, and Fs into Y in is 30. So, that is equal to 100 into X out plus 2 into 100 into X out. Y out has been substituted as 2x. So, this is 300 X out and that is equal to 30. So, X out is equal to 30 divided by 300. So, that is equal to 0.1. So, obviously, my Y out will be equal to 0.2. So, that is the answer. Right. So, the crux is you have to go for the balance over the whole cascade, which includes the recycle stream, in order to get rid of this recycle stream itself. So, let us solve this drawing problem. This is 2002 2 marks problem. What is the problem statement? It takes 6 hours to dry a wet solid. So, theta equal to 6 hours to dry a wet solid from 50% moisture content to critical moisture content of 15%. 50% to 15%. How much longer will it take to dry the solid to 10% moisture content under the same condition, right? And the equilibrium moisture content. So, theta how much from 50 to 10, and this 15% is Xc, critical moisture content, up to which the constant rate period is being maintained, right? And the equilibrium moisture content X star is 0.05, right? So, you see, this is the drying curve, and here we have to assume total linear falling section. So, this is X star, this is Xc, this is Xi. So, basically this is theta c, right. Now, theta, what we are going to calculate is theta c plus theta f. From here to here, this is Xi is equal to 0.5, Xc is equal to 0.15, and X star is equal to 0.05, right. So, theta f we have to calculate. So, theta c is 6 hours, directly we can write, plus theta f. So, you know that just I am writing the basic rate equation, n is equal to minus of Ss by this A into dx dt, right. A is the area. Now, Nc, if it is a constant rate, Ss by A, or rather we can write that theta c is equal to minus Ss by A dx by Nc from Xi to Xc. So, this is Ss by A, this Xi minus Xc divided by Nc is equal to theta c. So, theta c or rather this theta c divided by Xi minus Xc is equal to Ss by Anc, that we can get, okay. And theta c is 6 hours, this is 0.5 minus 0.15, that is 0.35, right. In appropriate unit is Ss by Anc, that we have to get in order to calculate theta f, you will see. So, here it is a linear function. So, see here it is Nc, right, this is Xc, this is X star. So, we can write that n minus 0 divided by x minus x star is equal to Nc minus 0 divided by Xc minus x star. So, n, the equation is Nc into x minus x star divided by Xc minus x star. So, next theta f is equal to minus Xc to Xf, right, Xc to Xf dx by n into Ss by A. So, minus of Xc to Xf dx this Nc into x minus x star into Xc minus x star, right, Xc minus x star into Ss by A. So, that is equal to Ss by A Nc into Xc minus x star and then ln of Xc minus x star divided by Xf minus x star. So, this Ss by Anc is 6 divided by 0.35 into Xc minus x star. Xc is Xc, what is Xc? 0.15 minus 0.05, that is 0.1 into ln Xc that is 0.15 minus x star 0.05 divided by xf. Xf is 10%. So it is 0.1 minus 0.05. Right. So you can calculate theta f from here. You add it to 6 hours, so you will get the answer. So always stick to the basic principle and very fast principle by which you can actually solve that problem if you are conceptually sound. So the next problem, see, this is 2007 2 marks problem. A 50 centimeter cross 50 centimeter cross 1 centimeter flat weight sheet weighing 2 kg initially, W initial is 2 kg, was dried from both sides. So total area is 2 into 50 into 50 centimeter square. In the constant rate drying period, constant rate, and it took 100,000 seconds for the weight of the sheet to reduce. So theta is equal to 1000 seconds and final weight is 1.75 kg. Right? So next question, another 1 meter into 1 meter into 1 centimeter flat sheet of the same material is to be dried on one side only. So here A, or A prime rather, is this 100 into 100 centimeter square. Right. Now the time required for drying from initial weight of here, this initial weight is 4 kg and final weight is 3 kg. So you have to solve for theta. So let's apply this equation, the same equation, which is theta c is equal to SS by ANC into this xi minus xf. Right. So you see, SS is what? Weight of the dry solid. That multiplied by kg of moisture per kg of dry solid gives you the weight of the moisture SS into xi minus SS into xf divided by ANC. So this is the initial moisture content, this is the final moisture content, the total amount, right? And the difference must be the loss of weight in the total weight. So this is equal to Wi minus Wf divided by ANC, which is 2 kg to 1.75 kg, so 0.25 by area. So this is in kg, right? So unit should be consistent. So 2 into 50 into 50 centimeter square into NC, and here theta is equal to 1000 seconds. So next, so NC we get as 0.25 divided by 2 into 50 into 50 into 1000, right? Kg per centimeter square per second, that's the unit. So next we have to go for 4 kg to 3 kg reduction. So theta is 4 kg to 3 kg 1, then denominator will be A is 100 into 100 into NC. Now this gives you 100 into 100 into 0.25 divided by 2 into 50 into 50 into 1000. So 2 here 2 cancels out, right. So 1000 divided by 2 into 0.5, that is 0.5, 2 into 0.25, that is 0.25. So it is answer is 2000 second. Right. The options were 1000, 1500, 2000 and 2500. So this is 2000 second will be the option. Yeah, another drawing problem. This is 2001, 2 marks problem. 200 kg of solid dry basis. So SS is equal to 200 kg. Is subjected to a drying process for a period of 500 seconds. So theta is equal to 500 seconds. The drying occurs in the constant rate period with a drying rate NC is equal to 0.5 into 10 to the power minus 3 kg per meter square per second. Right. The initial moisture content of the solid is 0.2 kg of moisture. So initial moisture content Xi is 0.2 kg per kg of dry solid. The available interfacial area A is 4 meter square per 100 kg of dry solid. Right, the moisture content at the end of drying. So it's pretty direct problem. So you see that theta is equal to SS by ANC into Xi minus XF. So theta is 500 second and weight is 200 kg. Area, now area is 4 meter square per 100 kg of dry solid. So for 200 it is 8 meter square. So 8 into this 0.5 into 10 to the power minus 3 into Xi minus XF. Correct? So 500, 5000 into 10 to the power minus 3 into 8 into 0.5 divided by 200 is equal to Xi. Xi is 0.2 minus XF. So this 10 to the power 3 cancels out with this. Right. 8 into 5 is 40. So 40 giving 5 here. So this 0.1. So XF is equal to 0.1. So the options are 0.5, 0.1, 0.05 and 0.15. So this is the answer. Yeah, that's all for this mass transfer problem solving session. In the next session, we will actually be covering this adsorption process.